part 2 of these notes. So, continuing section 14, doing an example of comparing proportions. So, here's our question. Are the proportion of left-handers the same among men and women? A simple random sample of 100 men and 80 women result in 8 left-handed men and 10 left-handed women. We pick 100 men independently, totally different sample. We pick 80 women. 8 of the 100 men are left-handed. P1 hat is 0.8. 10 of the 80 women, 1/8, 0.125, I think, is our P2 hat. 10 divided by 80 is the proportion of the sample of women who are left-handed. So, note the way the question is worded. Are the proportion of left-handers the same among men and women? Are they the same, or are they not the same? There's nothing in that question suggesting a one-sided alternative. Are men less likely than women to be left-handed? Sure. Are men more likely than women to be left-handed? Sure. But there's nothing in the grammar of the question suggesting that it's one-directional. So by default, it's two-directional. Are they the same? Yes or no? Are they the same or are they different? Are they the same number or are they different numbers? So the HA is going to be a two-sided test. If P1 hat and P2 hat are relatively close to one another, then H0 is plausible, and it's plausible that men and women are equally likely to be left-handed, that the proportions of them are the same. On the other hand, if P1 is a lot less than P2, then it would suggest that P1 is less. If P1 hat is a lot less than P2 hat, then it would suggest that P1 is less than P2, and vice versa, but only one of those is going to be plausible once we look at the numbers. On the other hand, if P1 hat and P2 hat are very different, then it suggests that P1 and P2 are very different. What do we have? So we'll run the numbers. 8%, 0.8, was the proportion of the sample of men who were left-handed. 0.125, 1/8 of the sample of women were left-handed. So in point of fact, the proportion of women who were left-handed was bigger in our sample. This might suggest that women are more likely than men to be left-handed. It might suggest that men and women have a different likelihood of being left-handed, but it certainly doesn't suggest that women are less likely to be left-handed. Do we have evidence that P1 is less than P2, that men are less likely than women to be left-handed? Maybe. Do we have evidence that men are more likely than women to be left-handed, that P1 is more than P2? Well, no, of course not. Is 8% suspiciously less than 12.5% in context? Maybe. Are they suspiciously different from one another, which is the question at hand? Maybe. Is 8% suspiciously more than 12.5%? No, of course not. So the greater than alternative is not in play here. The only reasonable questions to be asking are less than and not equal to. And again, it is the grammar that tells you, in this case sort of by default, that it's a two-sided alternative. So now we'll run the numbers. And this just says what I was just saying a moment ago. In context, 0.8 may be significantly less than 0.125, suggesting that P1 is less than P2. Perfectly reasonable question, but it was not our question. In context, 0.8 and 0.125 may be significantly different, which was our question, but 8% is certainly not significantly higher than 12.5%. So the greater than alternative is not in play. As always, if one of the two, less than, greater than, is a plausible question to be asking, then the other one is not. And the not equal to is always in play. So it's the grammar of the question that tells you whether it's one tail or two, but it's common sense that tells you which tail. And this just summarizes everything I've just been saying. Notice, by the way, we don't have to get too bogged down in which one we call 1 and which one we call 2. In the end, that's just going to change our logic. It's just going to switch things up a bit. If it's really going to bother you, then let 1 be the first thing that meets you in the sentence. men in this case, and let women be the second thing that meets you in the sentence. But ultimately, it doesn't really matter which one you call which. If we label things the other way around, well, in this case, the numbers might make it plausible that P1 is less than P2. That wasn't our question, but it could have been. I am not having any luck highlighting that unequal to sign, but you get the idea. But if we label things the other way around, make women 1 and men 2, then this would just swap the sign around. In other words, we go from a tail which is less than a negative z to a tail which is more than a positive z, or vice versa. It just reflects the problem back and forth. It doesn't matter which one you call 1 and which one you call 2, as long as you keep things organized properly. Of course, the 8, for instance, goes with the 100, and the 10 goes with the 80. So we'll organize our facts. We have x1, n1 is the 100, x2, number of successes in sample 2, sample size n2. Well, let's let x1 and x2 be the numbers of successes. So this is n1 and this is x1. This is n2 and this is x2. Unfortunately, the cruel reality is that we're going to need both the numbers of successes and the proportions of successes. We need the numbers of successes to figure out the bottom. And we need the proportions of successes to figure out the top. So let's organize our facts here. P1 hat is 0.08, P2 hat is 0.125, and the pooled sample proportion is there were 18 left-handed people out of the 180 people that we looked at, 0.1. Now bear in mind, more than any of the other sections, there is a lot of rounding error. There are a lot of intermediate rounding that goes on here. This particular example is jury-rigged so that there is no real rounding to be done. But bear in mind that you might be rounding this, you might be rounding this, you might be rounding this, you might be rounding this guy. So watch the intermediate rounding. If you have to round, the more often and the earlier in the process you round, the more it's going to throw off your answers. So keep an obscene number of decimal places until you get to the very end, and that will minimize the intermediate rounding. In the end, you only need z to 2 places. So keep 5 or 6 places throughout this entire process, and it'll minimize the chance that this z is off a bit by the end. Remember, the one thing we have going for us in hypothesis tests is that close is good enough. In the end, is the p-value less than 5%? Well, if it's 4.8% versus 4.7%, it's not really going to change the answer to that question. So the one thing you can say about hypothesis testing is that 9 times out of 10, close enough is good enough, but you still want to watch the rounding. So the pooled standard error we can get from the pooled sample proportion. The 0.1 times the 1 minus 0.1 square root of p times 1 minus p, square root of p hat times 1 minus p hat, where p hat is the pooled sample proportion, times the square root of 1 over the one sample size plus 1 over the other sample size. And because you're adding here, it doesn't really matter which one is which. Notice that nothing in the denominator really cares which one you're calling which. You're adding here, you're adding here, and you're adding here. So there's nothing in the denominator that cares whether you call men 1 and women 2 or vice versa. It'll all work out the same. And the only thing it will do in the numerator, if you swap the P1 and the P2 hats around, is change the sign on the numerator. So in the end, it's just going to change the sign on your z if you call 1, 2, and 2, 1. But we know by now that we're talking about tails. If it's a negative z, you look it up because the tail is to the left. If it's a positive z, you look it up and do 1 minus because the tail is to the right. Alternately, as we've seen, you make it negative and look it up. It comes to the same thing. So we'll run the numbers. We have the 0.8 minus the 125 on the top. Well, strictly speaking, that minus the theory of 0 divided by the pooled standard error, which is exactly 0.45 in this case, I believe. But again, watch the rounding. In the end, that works out to a z of negative 1.00. And this just summarizes what I said before about streamlining this process. The only necessary steps here are the H0 and the HA. Take the time to word them out symbolically. Otherwise, you'll be lost by the end. It's no good knowing at the end that you're rejecting H0 or finding evidence of HA if you have no idea what H0 and HA are at that point. So take the time to write them out. If you've got them symbolically, then you can recover the words easily enough. Theory and alternative. What is the z? Actually compute the z. Area of the tail or tails. Is it suspiciously small? Is it less than 5%? Whatever. Remember, if it's suspiciously small, if it's less than, say, 5%, you reject H0 and you find evidence of HA. So putting it all together in one big gulp, there's our test statistic formula, and there's how it's computed. And it's -1 in this case. The tail associated with that is 1587, but it's worse than that. Already it's not that small, but remember it's a two-sided alternative, so we want to double it. Assuming that men and women are equally likely to be left-handed, what is the probability of picking samples of these sizes and having this end up as much less than this as it is? Simply through chance. Well, 1587. But it's worse than that. The two-sided p-value plays out grammatically a little simpler. Assuming women and men are equally likely to be left-handed, what is the probability of picking samples of these sizes and getting statistics as different from one another as they are? At least as different from one another as they are. Both tails. So assuming men and women are equally likely to be left-handed, the probability of picking samples of these sizes and having the hats turn out as different as they did is 3174. In other words, it would happen about 32% of the time through random chance. And here I'm just saying that. Assuming men and women are equally likely to be left-handed, samples of these sizes will be as different as this 32% of the time. That's almost a third. It isn't remotely unusual. So how does our logic play out? Assuming H0, assuming men and women are equally likely to be left-handed, it just is not that strange for these samples to be as different as they are. Conclusion, there's no reason men and women shouldn't be equally likely to be left-handed. It is still plausible. Because this is not small at any reasonable level, it's not smaller than 5%, 5% level, it's not smaller than 10%, 10% level, it's not smaller than 1%, 0.01, 1% level. It's at any reasonable level, this is not what you would call suspiciously small. Nobody in their right mind would say that something that occurs 32% of the time through random chance is so unlikely that it makes you reconsider your facts. No, it could have happened. H0 is a perfectly reasonable explanation of events in light of the samples we happen to have. P-value is not small, not less than 5%, 1%, 10%, whatever. Well, 0.5, 0.10, 0.01. So do not reject H0, no evidence of HA. At the 5% level, for instance, it's not even close. Do not reject H0, no evidence of HA. It is still plausible that men and women are equally likely to be left-handed. We have no evidence of HA. That is to say, we have these samples provide no evidence. We have no evidence in the sense that we have these samples. We have no evidence that men and women are differently likely to be left-handed, that the proportions of all men who are left-handed and of all women who are left-handed are different. They could very well be, but this sample, these two samples, do not allow us to conclude that. H0 retains the benefit of the doubt. It's still plausible that men and women are equally likely to be left-handed in light of these samples. Therefore, because H0 retains the benefit of the doubt, HA doesn't come into it. HA only comes into it by the process of elimination, and nothing has been eliminated. Benefit of the doubt retained. Burden of proof not met. There's a section 14 example. I've got another example. Well, let's just finish it off. This is the same example, but a one-sided example. Using the same samples, do we have evidence that men are less likely than women to be left-handed? It is the grammar of the question that rewords the HA. Men being population 1, we're talking about P1 being less than P2. Now the question becomes, is the 0.8 suspiciously less than the 1.25? Before the question was, were they suspiciously different from one another? Bottom line, it is a one-tailed test instead of a two-tailed test. But everything is computed exactly the way it was before. -1, look it up, single tail, 1587. Because it's a less than alternative, because it's specifically not a not equal to alternative, we don't double it, we stick with it. It's still not close, but it's closer than it was. It would make a difference at the 20% level, but that's a ridiculous level to be using. You use it when you're asked to use it. But at the 5% level, no, 1587 is not less than 0.5. So again, we have no evidence of HA. We're not going to reject H0. In light of the samples we just did, it's still plausible that men and women are equally likely to be left-handed. We do not have evidence that men are less likely than women to be left-handed. HA. At the 5% level, we will not reject the theory that men and women are equally likely to be left-handed. We will not find evidence that men are less likely than women to be left-handed. Changes our perspective a bit. And of course, if you double a number, it's less likely to be suspiciously small. But in this particular example, it's not really close, whether you double it or not. Again, it would make a difference at the 20% level. At the 20% level, the one-sided thing we would reject. We would find evidence of HA. But back here, we wouldn't, because this is not less than 20%. So there's an example of a section 14 type problem. Take a look at the notes. Questions, put them on the discussion board, and we can do plenty more examples as people request them.